Welcome to the third IEEE Soft Robotics debate. I'm Sam Kriegman, a postdoctoral associate at the University of Vermont, and I'll be the moderator of today's debate among four leading experts in robotics. The debate's topic concerns biorobotics, specifically biomimetics, the science of mimicking nature's structures into technological artifacts, versus bioengineering, the creation of novel biological machines, or the assimilation of extant biological machinery into artificial systems such as robots. Bioinspiration can be found in most popular robots, such as Boston Dynamics Spot, which moves and looks like a dog. And for an example of an artificial yet biological technology, you need only look at my background, wood cabinets and a house. The bioinspiration and biofabrication and biohybrids are all connected intellectually and operationally. We're going to seek in this debate to find practical divisions. There are interesting distinctions we can make so that we can cut nature at its joints. The audience will have a chance to contribute their own questions through the Smartsheet app linked in the WebEx invitation. It looks like there's also a chat. I don't know if the audience can talk to the panelists through that. But we're also going to have the audience answer a WebEx poll. And this question is going to be asked in the beginning of the debate, and the very same question is going to be asked at the end of the debate to see how or if at all opinions change. And that question is, should we, that is a majority of the field of biorobotics, say 55% of the field of biorobotics, should we forego biomimetics and instead directly build robots using living materials that already possess the properties we seek? Once you've answered the poll question, sit back, relax, heat up your coffee, grab your leftover Valentine's Day candy, because we have a star-studded cast of panelists, and I'm excited to hear their perspectives on biorobotics and where they might disagree. So without further ado, begin with brief introductions using the ordering of the panelists from the poster advertising this debate. Cecilia Laschi will start, followed by Metin Sitti, then Talia Moore, and finally Ritu Raman. This ordering will rotate for each question. So Cecilia, please tell the audience who you are, where you are, what ideas you would like to discuss, demystify, or dissect in today's debate.
Okay, thanks for giving me the floor. Who I am, I'm Cecilia Laschi, as it was said, and where I am is also a relevant question this moment because I just moved. I am at the National University of Singapore now as a professor, and before that I was just moved from Scuola Superiore Sant'Anna in Italy. I was at the Biorobotics Institute, and my research is in soft robotics, so of course I started there and it's continuing here. And I started my research in soft robotics by studying an animal, the octopus. So in my case, my research, my soft robotics is very much related to bioinspiration and biomimetics. So I think that in general, soft robotics owes a lot to bioinspiration because it is in a sense bioinspired per se, because what we learn from nature is that we have to use soft bodies, soft materials, compliance in robot bodies, and that is exactly soft robotics. And of course, the question whether using biological tissues of cells in biohybrids for building soft robots, it makes a lot of sense today. Where I see a little difference is that biohybrids are good when you want to build, for example, an actuator, and for sure it can be better in terms of performance than an artificial actuator that wants to mimic a muscle or a biological one. So in terms of components, but soft robotics is also very much also about design, about robot design, and then in that case you cannot really have hybrids.
Thank you, Cecilia. Metin, you're next.
Thanks. Hi, everyone. I'm Metin. I'm a director at Max Planck Institute for Intelligent Systems in Stuttgart, Germany. My brief background is I did a postdoc at UC Berkeley, and then I was a professor at Carnegie Mellon for 12 years. Then I moved to Germany around 6 years ago. My group specializes on small-scale robotics. I have been working on Bioinspiration since 20 years or more. And biohybrid systems also last 13, 14 years. Since small-scale systems are highly limited with their size scale and a lot of onboard capabilities, we have been looking at ideas from nature for learning ideas. That's where we did the bioinspiration a lot in locomotion, dynamics of animals, how to adapt it to robotic systems. And also we figured out that when we want to go really, really small, bioinspiration was not sufficient or was not easy. And we figured out biohybrid systems, like using organisms themselves or live cells as actuators, as sensors, even as controllers, could be a great solution for miniaturization of robots. And if you can integrate them, of course, to robotic elements so that you can control them. So that's what we have been doing. Another aspect of my research is in physical intelligence, so how to embed intelligence into the body of the robots. So that's also where we can learn from nature in the sense of bioinspiration, but also we can again integrate biological life cells to create physical intelligence on the robots. And finally, we would like to do medical applications of these tiny robots. And there, the materials become very important. And naturally, for us, biohybrids are very interesting because they are typically, if they are taken from especially the patient's body, they are fully biocompatible, they can be biodegradable. Those are very important. And also, they are very small, of course, again, because of size scale, can be even cell scale. Then we have a lot of, in that sense, uses of biohybrid systems for medical applications that I'll talk maybe later a little bit more in detail.
Talia?
Yeah, hi, thanks. I'm Talia Moore, and I work in biomechanics, bioinspired design, and also now soft robotics. So I'm an assistant professor in mechanical engineering at the University of Michigan. I'm core faculty in the Robotics Institute, and I'm an affiliate in the Ecology and Evolutionary Biology Department and the Museum of Zoology. So my background really comes from biology and biomechanics and evolutionary biology and like community ecology. But I've been working for a long time in bioinspiration specifically. And bioinspired robotics to me is kind of like this broad umbrella that includes like biomimetics and biohybrid and lots of these different areas. I think it's like a very like integrative and beautifully expansive kind of field. In my work, I examine the biomechanics and the evolutionary history and the community ecology of animal features to understand how animals adapt to selective pressures or challenges. And then by understanding the mechanisms underlying the biological solutions, we can apply these principles to human problems. So yeah, I think that it's a pretty incredible source of information and inspiration to build these things. I think biohybrid work I'm less familiar with, and I'm excited to learn a lot more during this debate. Yeah.
Thank you. Ritu, you're up.
All right. Well, hi, everyone. My name is Ritu Raman. I just want to start by saying that I'm so excited to see all of these faces, because sometimes you read papers for so long and you have like a certain vision of somebody. So it's really nice to interact with everybody in person. But yeah, my name is Ritu Raman. I started exploring biohybrid design, which is my field, during my PhD at the University of Illinois with Professor Rashid Bashir. So I spent a few years building locomotive robots powered by mammalian tissue and specifically engineered skeletal muscle. But then I spent the last few years as a postdoc with Bob Langer at the Koch Institute, really thinking about the next generation of medicine and what kind of tools we'll need to solve those. And so both those experiences kind of inform both how I define, bioinspired, biohybrid, soft, and also what I think the future of the field should be. So for me, if we think about, I guess starting with the definition, if you think about like picking up something and holding it, the soft part is the fact that we're like compliant and can get a good grip on things of weird shapes and different conformations, right? And I think both bioinspired and biohybrid are the same in that they're saying like, how hard am I gripping this so that it doesn't drop? Or if it were oily, I would sense that and know to grip it a little bit harder or in a different way. And whether you do that using abiotic materials or biotic materials is really, I guess, the question of this debate. And I don't think there's an obvious right answer. I mean, there's times where Kevlar is better than your skin, right, at preventing you from getting burnt, but there's also times when you can rip a Kevlar vest and it's not going to heal, and you can rip your skin open and it is, and that's awesome. So I think that the real question is, we should be designing for the problems that we have and not be constraining ourselves because of the materials we have available to us. And to me, I feel if we neglected biological materials as building blocks, that would be a really big problem, especially in medicine where cell therapies and gene editing are really the future. I think that integrating biological materials into machines is it's just something that I think we have to do. But I wouldn't be upset if people in this room proved me wrong, because I think, we just all want everybody to lead safer and better and healthier lives. So if that doesn't need to happen biohybrid, that's okay with me. Thanks.
Thank you. Okay, so now that we're all acquainted and somehow perfectly on time with this debate, I'd like to get a sense of how the panelists view the current paradigm of biorobotics writ large by asking a kind of meta question. What is the single most important open question in biorobotics today? I realize this is a very weighty question. It was sent out to the panelists beforehand, but I also understand if you might have not gotten around to that or it got lost in your emails. But Metin, if it's your turn, if you have a prepared answer, otherwise we can come back to you.
I will all improvise because honestly, these are things we have been always struggling. It's always hard to say what is the one most difficult thing because there are so many. So you need to pick the most challenging one. But I think if you look at our field, it's been mainly in designing first, right? So we need to come up first designs of biohybrid or bioinspired or none of these approaches to solve our problems, right? In that sense, I think in the design methodology itself, everything I think we will see that they are not solved fully in soft robotics field, especially. Design methodology is one thing I see still. We don't have a very advanced tools to both model and immerse design. I mean, basically you say what you want to achieve and you have a tool that will tell you what kind of soft robot you need to design inspired by or integrated by living cells or inspired by nature or something fully different. We don't have such methodological tools yet. That's one big problem. And actuators and materials is a big problem in this field. There are a lot of great developments in the last 5 years in the sense of actuation and smart materials, smart responsive materials. But there is always a big space of how to make the multifunctional self-healing, let's call them physically intelligent in my case, physically intelligent materials that can not only have specific function, but can adapt, can perceive, act, and adapt or learn even in the higher level, compute, memorize. So those kind of really pushing the boundaries of simple single functions to really a lot of them that we see in biological systems. Can we get there? So those are two things I want to bring up. There are more, but let's stick to those two of how to design soft robots in the methodological ways, and then how to get really physically intelligent materials to enable more advanced, complex soft robotic and other robotic behavior.
Thank you. That was great. Talia?
Yeah, so I agree a lot with Metin. I think that like the first big idea that that we can try to address is this idea of how to embed multiple functions such as like actuation, sensing, and control into materials, and yet still have something that's simple enough to build. So you can think of putting all of these things in, making something kind of autonomous, and it being just like this incredibly complex thing with lots of wires and lots of control and all of these different like valves and things or cables pulling everywhere. But biological things can do this with ease and can embed all of these different functions in the same system. And we can see evidence of this when we see portions of animals that become autotomized or that break off on purpose. So for example, like a lizard's tail can sense an attack. It can break itself off and then start writhing around without input from the central nervous system. More in Cecilia's realm, there's an Argonaut Octopus, and the Argonaut Octopus is capable. It has this one very long tentacle that's actually a penis, and it can break off, swim towards a female, and inseminate the female. Like, we don't have soft robots that can do anything near like those types of kind of autonomous movements that include these complex functions like sensing and like actuation and control. I think that that's pretty exciting, and that's the kind of thing that I want to shoot for. I think the other two big ideas we need to think about are like ethics, and not just ethics of, you know, where are we getting materials from, but also how are we thinking about like recycling and reusing these materials. So that's something I think we can talk more about. I think there's a question about it later in the debate.
Thank you. Ritu?
Great. It's hard to follow these things. I think, so I will start off with a more mundane version of what I think is, you know, a big remaining problem, and then boil it down to why scientifically that matters. And I guess the mundane part is that, you know, there is a business side of science, right? And like we can only do research that is funded, and we can only get funded if people believe that something matters or is valuable or impacts their lives in some way. And so I think, you know, a lot of people, when they think of robots, they are thinking of more harder systems, or if they're thinking of something that's more bio-inspired, they have the Boston Dynamics dog and it's like jumping up and down and they have this great vision. But I think that we have to prove to people that there's a reason to be working on things at a smaller scale or that integrate biological components, and we're far away from that. And I think part of that, you know, yes, that's a social problem, but really it's a scientific problem that we have to address, which is that we have to convincingly prove to people that there's a reason that these systems might be better than others. And I think we prove it to ourselves all the time, or like we understand when we've made a really big leap in something, but maybe we haven't done such a great job of convincing others when there's a technical advantage towards doing something bio-inspired or biohybrid. So, you know, part of that during my PhD, I was worried about that a little bit because we had made these robots that used engineered skeletal muscle to move and walk around, and like, yeah, they make really cute videos, but compared to the Boston Dynamics robots, it's very slow, right? And it doesn't move very far, and it can't do as cool things as that can yet, even though it's this big technical accomplishment that those of us in the field know. And we tried to do a little bit to show that it could do things that synthetic robots couldn't do. So things like exercise and get stronger, or heal after it had been damaged and completely recover forced production. And I think that those have gone some way towards proving that. And I think the next step would be not only actuation, but as Talia and Metin were mentioning, you know, sensing and control is really the next, I think, big technical frontier that has to be managed. So things like sensory feedback, integrating that with autonomous processing and making some sort of decision making and programming that in a way that is ethical is going to be, I think, the next big technical challenge. But it starts for me from the social challenge.
Cecilia?
Yeah, so I want to go back to Metin's point because I couldn't agree more on the lack of formal methods for designing bio-inspired robots, and this is very important for a discipline to progress really. And I want to go, to the root of this. We also lack a definition. So what is bio-inspiration? The word bio-inspiration is vague. It's a vague word because it wants to mean that you are inspired and your creativity is stimulated by something, but it is definitely vague for science. So, and where I see it is, I do several reviews of papers, and I see a lot of claims about bio-inspiration that are so different from a paper to another. So in some papers, in some works, bio-inspiration means that there is a biological study and biological insight, and some principles are understood and used in robotics, maybe in a robot that in its appearance is completely different from the original model. And some other works where it's just maybe the external appearance or just a vague inspiration to an animal or something, but in the end it's just robotics, it's just technology, and I don't find any biological insight. But if we use bio-inspiration, that's fine because it's just an inspiration. So what I want to say, sometimes I see a robot with 5 legs or 5 limbs of any kind, and it's a starfish-like or starfish-inspired and things like that. But again, if we don't have a definition, if we don't have a clear method, a clear process for designing something that can be named bio-inspired, we just follow trends. There are trends in science also. I remember that many years ago, using the word bio-inspired was detrimental in robotics because it was something like it doesn't work well. So it's not precise, but it's bio-inspired. So it was sort of justification and excuse. Now it's the opposite. It's very trendy, so everybody say, okay, my robot is bio-inspired in some way.
Thanks, Cecilia. So I wonder, maybe it would be useful if anyone has a good definition of bio-inspired robotics that they think is particularly useful for their research. Let's hear it.
Sure. I mean, I taught Bioinspired Robotics at CMU for a while, and it was one of the most popular classes. And I agree with Cecilia that, I mean, in science, there are these trends. I mean, bioinspiration is one aspect. Now, soft robotics, nanotechnology, energy, graphene, you will have always these popular hot AI now, machine learnings, right? So these are all things as what we call trends come in because of funding agencies, because of a lot of political reasons, indeed, they come up. And bioinspiration, by the way, bionics has been really old field. I mean, in Germany, where I now more interact with people, bionics has been around for 90 years, and there are really bio-inspired products enabled by designing furniture and many things, architecture. So these are all great examples, but then how do you define it as a scientific principle? And what I try to say is like adapting the principles of biological systems into engineering systems. So it's not about mimicking. I mean, that's what we call it bioinspiration. So also there is always this debate. Is it biomimetics? Is it bioinspiration? So again, mimicking nature is really, really difficult and almost impossible. And even if it was possible, the question is, why should we do it? I think if you look at the way we approach these bioinspiration, biomimetics, biohybrids, everything, because we are trying to solve problems, all right? So we have engineering problem. We need to design. I mean, in my group, the dream is, can we build a fantastic voyage robot inside the human body that can go everywhere and do this and that? So with that dream, then we ask, like, which approach should we take? And is bioinspiration one of the approaches to solve this problem of building a device that can operate inside your, let's say, brain? And the answer is, yeah, sometimes it's a good approach to look at and learn from. So it's in that sense, not mimicking what biological cells do or animals or organisms do, but can we learn from the principles of operation? This could be locomotion, this could be how they control sense and intelligence and self-healing and many properties, and can you adapt it to a synthetic system with the capabilities we have in the given material chemistries, in the given complexities, fabrication techniques, all these things. That's why adaptation is the main thing of the principle. Again, that's why we need to identify what's the unique principle behind given biological behavior. So that's one aspect. So the second aspect, why bioinspiration is popular is, I tell my students, if you want to get in the top scientific journals, do something bio-inspired. It will be easier. If you just do pure robotics, you will get into translational robotics, which is a great journal, but you will be not in these fancy journals. The reason is because bioinspiration research can enable you to build robots as a model system to also learn about biology. That's where the second part of this, how we learn from biology and adapt to engineering systems, and how engineering systems can help to biology. So that's what we call the loop of interaction. So that loop makes it more scientifically interesting. So forgetting the buzzwords and the trends, I think if we can really build inspired robots or devices that can do as function and performance-wise really interesting things that other designs can't do, and then these devices we learn about how the biological systems work. That I think is a great scientific, to me, field where you can define in these kind of more principles of locomotion and other behavior, and learn from them, and then use that knowledge to also understand biology better.
Yeah.
Thank you, Metin. Go ahead.
If we do claims for bioinspiration that are not fully supported by science and technology, then we are going to disrupt this loop, this interaction loop that you were describing. So this is exactly my point. We must be very solid in order to interact and collaborate with the scientific communities related to our bioinspiration. Yeah.
So I completely agree with both Cecilia and Metin. And so the way that I think about bioinspiration versus biomimetics and other kind of like vague inspiration is, if you are doing biomimetics, you're trying to mimic something without considering its evolution potentially, or without considering how it fits into its environment. And so this is something that we might call, from an evolutionary perspective, adaptationist, which means just because it exists, it must be the perfect solution, which is not always the case. And so if we consider evolutionary biology and understand kind of the selective pressures and how a thing evolved, we start to learn more that there are many different reasons why something that we see in nature might be non-optimal. So for example, like a peacock's tail, right? It's very beautiful. It's useful for sexual selection, for attracting mates, but it's not actually that great for flying. It hinders flying a lot. And so if we study the animal, we might say, okay, we understand now how it hinders the flight, but our robot doesn't need to attract mates. So we can remove that constraint and actually surpass the performance that we see in nature using bioinspiration. And it's the key there, as Metin said, is by extracting the principles underlying the behavior that we see, or underlying whatever the structure, whatever the principle is that we're trying to extract. I think that's really important.
Definitely. So this is what I teach my students in computer science or engineering. I say, okay, when we observe a living being, we should assume that it is not the optimal solution, because it's the result of evolution. So it's like you design something that for some reason doesn't work well anymore, and you modify it, but you can redesign, rebuild it from scratch. So it's just putting patches. So in terms of well aware that that's not the optimal. It's never the optimal.
I mean, that's a great point. That, I mean, again, like, let's say if you want to build an opener of whatever, a bottle. I mean, why should you look at nature? I mean, looking at nature should be really when we have really complex problems that are not possible to solve easily in an abstract way, or it's in an unstructured environment that like biological systems are, so that it's so complex that we can learn from unstructured environment behavior and principles. And as we say also, biological systems are not perfect because evolution is limited. I mean, we don't have rotary joints, is that right? Except the bacteria flagella motor, because of biological limitation. And so bioinspiration is only one of the approaches you can learn from as engineers or as whatever scientists, but it's not the only way. And also, as we say, like, I mean, you mentioned a peacock example, which is a great one. And also a jellyfish, for example, you make a soft swimmer, but jellyfishes shouldn't just swim. They need to also catch prey. They need to also do many other functions. That mating and many things that robots right now at the moment don't need to do, at least for now. So that, you know, these are maybe biological requirements that makes the optimization of the given principle in much more broader way than our more focused engineering problems. So that's why a robot doesn't need to do all of these things at the same time. To me, the big problem of biological systems, they need to be general. They need to solve everything in general environments. They cannot be specialized too much, otherwise they will not survive, and depends again on which type of environment. So the constraints of the biological systems and the engineering systems are not always the same, let's put it that way, and the functionalities. That's why copying nature is really a big mistake that, yeah, we just need to see where we can take something useful that makes sense and we isolate correctly. As you say, a nice beautiful feather, but you cannot fly anymore, so not a good thing for a flying robot.
I just wanted to say that I actually find this discussion very clarifying, and it's changed my opinion on something, because for the longest time I've been saying, you know, bioinspiration is reverse engineering. You're recreating what already exists in nature, but biohybrid design or biohybrid engineering is forward design. You're creating something that hasn't existed before and creating non-natural or hyper-natural functionalities. But after hearing the three other panelists talk about how Bioinspired doesn't nearly actually need to mimic something in nature, or doesn't assume that it's the optimal solution, I think that changed my mind a little bit about it, and maybe I will reconsider how I talk about it in the future. Oh, I also wanted to say that Talia's website, her lab website has a beautiful diagram where she describes it as robots for biology and biology for robots. And I think that says it in a very brief way what everybody is trying to share. So she didn't say it, I was hoping she would, so I'm highlighting it.
Thanks, Ritu. The other thing I wanted to say is I wanted to make a quick plug for biomimicry as well. Because I think biomimicry can also feed back into the loop of learning about biology. So in some of the work that I do, it's animal-robot interactions. And so it doesn't really matter how the animal inspiration was able to actuate. I'm just trying to copy how an animal looks, like a prey animal looks, and how it acts, so that it can be close enough to that inspiration that it can fool a predator. And that's helping me understand how predation works. And so this is an example in which biomimicry, not bioinspiration, can still feed back into learning more about biology. So both are still very valid.
Yeah, I fully agree, Talia. The challenge is, though, isolating the right behavior in the robotic version with all these other requirements that biological systems have. And for example, if you just want to optimize the flight of the wings of an insect, you need to find out how to isolate that robotically and focus on only that. And so that part is, I mean, as you say, because robot behaves there as a model of the biological system. But when you have a model, you have to just simplify or choose some aspect of the biological system. You cannot copy everything. So that part is really always a big scientific challenge. How can you isolate the right, or how can you create the right model that can really replicate the behavior, which in a complex system where you simplify. So that's always, yeah. But that's fun. Yeah, that's a fun part of the science. Yeah.
That's a great challenge. But once you do identify which features you want to alter, the amazing thing about robotics is that it can allow you to create combinations that may have gone extinct, or creations that may never have existed in the fossil record or in evolutionary time. And so you can actually explore this kind of functional morphospace and use robots to test hypotheses and understand more than just studying the animals themselves would have allowed you to. And so that's what I find really exciting about studying both bio-inspired robotics and biology together.
But I want to ask how we can go past this kind of ad hoc mimicry, or bringing in, identifying these traits that we like in our robots, which ones are adaptive, how we remove them from the proximate mechanisms that were just overly reliant on the materials that nature had at hand. How can we systematize this process of finding the ultimate mechanisms that are really going to be useful in our robots? How do we create a real science of bioinspiration?
I think if this is a formal question, is it my turn to go first, or should I wait for someone else to go first?
Anyone can answer. Talia, what do you think?
So I've been teaching bio-inspired design and for a couple of years now. And I think that the key is really to train biologists and engineers together and to train them kind of in the same classrooms, train them with the ability to communicate with each other, and teach them kind of what the other discipline finds important and interesting. And so not every person needs to know everything, but you need to know enough to know what you don't know so that you can ask someone to build a complementary team. And so I think when biologists and engineers work together, they can come up with these amazing ways to leverage what they find in biological systems and apply them really beautifully. The other thing too is I think that it's really important to continue to discover. So making original discoveries, finding out how the world works, we may find something that we never even knew we needed. And then once we apply it in the real world in some sort of engineering solution, it becomes this game changer. So like Velcro, for example, right? That's a bio-inspired design. It comes from the cockle burrs from this plant that got stuck in some Frenchman's or Swiss man's dog, right? And so he studied it and he made Velcro. It changes our lives forever. But if you were looking for an adhesive solution, you may not have been able to find that inspiration. But just by examining the natural world, you can find unusual solutions that may change the world.
Yeah, I mean, just to add that, I mean, Catherine's question, so Sam's question, sorry, that, I mean, we talk about underlying principle as we have now in Talia's example, Velcro. I mean, basically the scientific part, as we say, I think the big issue in the bioinspiration is, I mean, even my students sometimes say, okay, one animal inspired and did something, okay, next animal and next animal, so what? What's next? And plus, like, okay, what is really the science behind it? I think really it's all about the underlying physical and also biological and materials behavior. Like, can we define the mechanics of these structures? Can we define the dynamics of locomotion in water? Because the locomotion principle, swimming behavior in water is the same for animals, same for robots, same for everything, because the same physical principle. That's why animals evolved to find some of these solutions. And as also Talia mentioned, they cannot cover all the solutions, and then we can also discover other ones. So in that sense, it's really all about like, what are the underlying physical principles that we can isolate, abstract from the animals, that we can study and then replicate them or even create them in synthetic different versions with the same principle. I mean, you can make a Velcro, but doesn't need to look like exactly Velcro, but the function of the attachment of male and female holding each other mechanically, if you understand the principle, you can just build a synthetic version that uses the same method. But it's the methodological similarity, not the copying of the same morphology or same material.
Kind of building off this fundamental understanding piece, You know, I'm trained as a mechanical engineer, right? And I think the same way that mechanical engineers have interacted with other more basic science disciplines like material science in the past can also inform how we do bio-inspired or biohybrid design in the future. So if you think about, you know, in mechanical engineering, what you're taught is if you have a piece of metal and then you push like this on it with this amount of force, it's going to change that much, right? And you're taught the input and you're taught some sort of transfer function, you're taught an output. You're not necessarily spending a whole ton of time thinking about the crystal grain structure or the molecular arrangements. And you don't need to know that, but there are other people in physics and material science that do need to know that and are contributing that piece to it and telling you what that input to output ratio is or behavior relationship is. And I think similarly with biohybrid design, for example, I've been teaching a class where you know, we teach people how to make their own robots that are powered by muscle, and the students ask very different questions based on their backgrounds and their goals. So some people might be more interested in what are the underlying chemical, you know, mechanisms or biological mechanisms that are defining how the robot is getting stronger, and what does that teach us about muscle or neuromuscular junctions. And there are other people that are like, how can I design a skeleton that can deform the most in response to the same amount of force, because I'm interested in design mechanics. And I think Talia mentioned earlier, like not everyone needs to know everything. And I think that that's very true, but perhaps one way that we could arrive at a common skill set is saying, you know, there's an input, there's a black box in the middle, and there's an output, and you can pick where you want to be and dive deep in that area. But if we all populate each area and then have that combined framework as a whole, we can have a set of rules or design rules that we can work with to build these kinds of machines.
That's a really nice vision, Ritu. I want to ask maybe if we can try to be a little bit skeptical in this next question. Is there and will there remain a place for non-soft, non-biological, non-biomimetic robots? Which of these do you think will kind of fade away as not being a useful kind of mechanism for future robots? I think that Talia is up in our ordering here. You're muted, Talia.
I think it depends on your definition of what a robot is, right? So is a robot just a mechanical system that is maybe a little bit bio-inspired? I mean, if we look at the origin of the term robot, right, it comes from this play in which there were human actors playing the role of robots that were doing undesirable tasks for the actors playing humans. And yeah, I mean, I think that that's maybe not the case. Like there are robots that are not bio-inspired. And I think that they're still really useful, especially when you want to have like long-term use, durability, easy modularity for repairs and precision. So one of the most important robots that I think is in use right now for our society is a pipetting robot, right? It can pipette like, you know, 50 aliquots of a liquid simultaneously over and over again for years. And that's how a lot of molecular and cellular biology gets done. And I think it's one of the most important robots, I think, that serves a role right now in society. So yeah, I think that there's no reason we would want that to be soft or bio-inspired. So for certain tasks like that, I think that rigid robots that are non-bio-inspired are probably going to stick around for a long time.
It's interesting. Do you think that, Talia, that biological or soft robots could be useful in a very predictable, structured environment like a factory that rigid-bodied robots excel? Do you see maybe there could be a use for bioinspiration there in the future? And if so, what do you think?
I think that when it comes to collaborating and interfacing with human workers in that kind of factory environment, yes, because I think that it helps with safety. But if you have a fully lights out factory where everything is fully automated, then no, I don't think you need it to be soft.
Great. Ritu?
I definitely agree with that. I mean, and I answer it definitely yes to the question. So of course, robotics will be there. I mean, I think robotics is a fantastic discipline because it is young, but it reached levels of performance. If you look at the robots in the manufacturing, the hours they can work without any failure, the accuracy they reach. I mean, that's really fantastic, and I don't see any reason to waste of this wealth of knowledge that we have built, and that's fantastic. The Bioinspired approach or soft robotics, they come up when there are limitations in the other technology, and it is especially in structural environments, as we said, and not in manufacturing, not in the industry. Probably in the industry, yes, it can be helpful when there is interaction with humans. Also, when there is something unstructured like manipulation of objects, like the food industry, where it's not everything so well structured. So in my opinion, my own experience and my own history, for me, bioinspiration and soft robotics have never been sort of replacement of robotics, but just some complement. And when someone asks me, how do you see the future of soft robotics? My provocative answer was, I hope it disappears, because it's not, this word was born to exactly to say it's not the usual robotics, something different, it's soft robotics, but I hope that it will be just integrated in robotics. So it will just be the way we design and build robots in the future. Soft when they need to be soft, with some compliance when we need some compliance for making them work better. We learned this from nature, basically, and we learned that compliance is not something to fight, but it is something to use sometimes, and this is just the lesson that we have to keep in robotics.
Thank you, Cecilia. Ritu?
Yeah, I think that it's certainly, I agree with everything that was just said about, there are environments where it's very obvious that you would want to use something that, might not be soft. But I also think in environments that we're typically used to thinking of, like, it's so obvious that we should do biohybrid or something like inside the body in medicine, there are times when that level of complexity is just not necessary and not warranted by what you actually need. So for example, medicine is what I know best, so I'll give a couple examples in that space. So if you think about something that's like triggerable, senses some trigger and then like does some outcome. I was supposed to help this team of surgeons in my lab a couple years ago. They're placing all these devices that are inside your stomach for a certain period of time. They're either sensing, they're releasing drugs, they're doing stuff. Sometimes you have an allergic reaction or you're done with the thing and you don't want to be put under and go through an endoscopy and have that thing taken out of your stomach. So they were like, can you make it out of some triggerable material that breaks down at a certain time? And so we, took a bio-inspired or mimetic, I guess mimetic in this case, approach to make a material that could sense the light and go through a conformation change and essentially help these devices pass through the body when you shine light on them. And I think that there was no reason for us to, we used a hydrogel with like a certain chemical linker that changed conformation in response to light, and it worked just fine. And it was simple and it was safe and it worked inside a pig, and that's pretty hard, right? So in that case, there was no reason for us to bring something biological or biohybrid necessarily into it. However, there are certain cases, for example, out of my lab, there's a new cell therapy company company where you implant these living cells as sort of chemical factories, and they can sense changing levels of insulin in a patient's blood and change how much, or changing levels of sugar and change how much insulin they're secreting in response to that. Now, that I think is a situation where it's much harder and maybe even impossible to replicate using synthetic materials, and so the level of complexity that's warranted by biological materials is necessary. Versus in the other implant case, could I have genetically reprogrammed some cells to respond to light by secreting proteases, which hacked up a matrix and then did this? Like, I could have done that, but there was no reason to. And I think that's kind of where you have to ask yourself as an engineer, when are you answering a problem with an over-engineered solution versus when are you using something that is the absolute minimum to get the safe and efficacious response that you want? So I would say that even in the realm of medicine, there is a role for both non-biological and biological systems depending on the application.
All right. As we all, there were all great comments, and just to add on top of them, I think one thing we should be clear is bioinspiration, biohybrid design, or any other approach. These are approaches to solve our given problems, which are typically complex. So in that sense, there is no one winner. There cannot be one winner. There cannot be all robots be all soft, all rigid, all bioinspired. So we are only looking at these approaches to get ideas of new design and inspiration principles, or more adding more complexity by integrating live cells. In that sense, in my group, we work on all of them in parallel because none of them is a winner or cannot be a winner, because for a specific problem, they might work great because everything has pros and cons. I mean, soft systems, there are things they can do, there are things they can't do. Same for biohybrid systems. So in that sense, the future is always, there is space for everything, because diversity of approaches is always essential to our tools to create new functional devices in complex environments. Your point on an industrial line. An industrial line is a structured environment. You can make many things in a much simplified way than outdoors where things are uncertain, unstructured. So that's why, to me, all these approaches are especially essential for solving problems in unstructured environments. So this is inside the body or outdoors or anywhere that you cannot go and structure how the robot should function, interacting with people. So you cannot structure it that well. I mean, because we have a lot of uncertainties and changes in the environment. So that's why I think in those unstructured cases where we need all these approaches, but there is always space for new approaches because none of them can do it the best way. They can only do a good enough way in an optimal, suboptimal way. And again, depends on the application, as we heard. There could be some of these approaches better than others, but there is no, I mean, we have so much variety of applications anyway, so that we need to always have these different tools that we can build new robots every time. So that's why I mean, and that's the also rule of nature, right? So if there was one winner, evolution will be not interesting. So diversity is always the essential part of life also, so that we can be robust, we can really get into new approaches of solving problems in different ways than we can. Because, for example, there are many things we are right now neglecting in our society. All of the robots are now built, they can take all resources they want. They are really, really non-environmental, non-ethical sometimes. So really, when we get into the levels of society where we need now everything green technology, all the robots should degrade after their lifetime is over. So these kind of requirements will come into play, and then we need to develop new approaches and new techniques to make maybe degradable robots, or robots need to self-replicate one day maybe, or whatever things we will see that they are really needed because they need to survive in space environment. So these kind of things are always will happen and will change by time. That's why we always need new approaches, and any of these approaches we are talking today will be never the only one. But they are great ones to just study now and learn from, and create tools out of them, as also Cecilia mentioned, but they will be not the only ones, so that we shouldn't have that kind of perception, because our researchers instead of sometimes think, oh, soft robotics is everything, it should solve everything. So this is the problem of, you have a hammer, you're looking for a nail approach that, we have all these great hammers, but you need to have a lot of set of hammers and that will help us to solve a lot of different problems.
Thank you. Okay, one last question, a formal question. It's very related. Biohybrids and soft robotics remain hot topics, but they cannot remain so forever. What aspects of robotics do you think will emerge or is emerging that will extend, replace, complement bio and soft robotics research?
I think it's my turn. So I'll go. I think it already got a shout out earlier during the debate, but you know, I think the new hot topic is AI and machine learning and all of that sort of things. And I won't pretend to understand it, but I do think that it's a sort of thing that we need to learn to understand with and communicate with, because it is going to be, it really ties in very well with what I see as the big next technical challenge of our field, which is control, autonomous sensing and control. And so if you think about the fact that a lot of this you know, neural networks disciplines were inspired by biological neurons, right? And how they communicate with each other. And they've essentially simplified it as like input, output, in yes, no, activation, inhibition, or summing different outputs and making some sort of decision. All of those principles are derived from biology, but they are derived from simplified biology. And so as we develop more understanding of, say, how sensory neurons and motor neurons are interacting with each other, or how interneurons are mediating that you know, interaction, or how they're telling our muscle to move, we're going to develop more of these sort of transfer functions. I'm going to keep using that phrase of like, how do you mediate an input to an output? And as we develop that, I think we need to be talking more to folks in the AI space and thinking about, you know, how do you define autonomy? How do you program it? And then how can we do it using actual neuronal networks and not just neural networks? So for me, I think that is the next step. And certainly, you know, we talked about computation and learning and memory, and all of those things I think are tied into that. So I think that's the next big thing. And for me personally, the challenge will be cultivating the literacy of that space and the language to be able to talk to those people in a meaningful way.
Cecilia?
Yeah.
What do you think?
Yeah, and AI is definitely one of the aspects. What I see also missing in soft robotics, and this boom of AI could help, is the development of, let's say, high level of control or intelligent behavior in soft robots. This is something that is very common in robotics. I mean, roboticists are very good at developing intelligence inside the robots, which means the level of intelligence required to have an autonomous behavior. But in soft robotics, we don't see much of this. And on the other hand, I think it's very interesting because we have a body that can deform, it can squeeze. So when how the robot can the robot decide how to squeeze the body, how to deform it, how to make it move, how to stiffen some parts. So extremely interesting from the research point of view. But another aspect that I see could bloom in the future is energy. I mean, today new forms of energy are studied for many reasons. There is a lot of research on batteries, new kinds of batteries, or hopefully something different from batteries in the future. And it is done for other reasons, not for robotics. It's for the electrical cars, or I mean, for many other reasons, but I think it's an aspect that is relevant in robotics as well. It's very relevant to robotics, so this could be one of the hot topics in the future.
So, I mean, this is, again, an interesting question that I like to answer, but also I hate to answer, because one thing I really like researchers to do is don't follow the hot topics, please. You know, Please have fundamental research questions and work on those fundamental questions. And of course, hot topics help you to get funding and maybe whatever visibility, but shouldn't be the driver, should be just a mean for you to do what you want to do. So looking from that perspective, of course, these things will come and go. I mean, as I said, in my lifetime of academia, nanotechnology was a big boom, energy was a big boom. As I said, biotechnology is always a boom. I mean, there are all these kind of hot things that are somehow how to say, supported by governments and funding agencies because of different needs of the societies and whatever reasons. But while we are conscious about them, again, we should really ask the fundamental questions and follow them. Coming back to fundamental questions here in robotics and these areas is always, of course, you know, as I said, designing these systems and energy source is, as Cecilia mentioned, is always a big problem. That especially when you miniaturize robots or have more durable long operation times, energy source is always a big problem. How to harvest energy from environment, how to make environment-friendly robots. As I said, like really, that's a very important field that needs to be more and more emphasized. Unfortunately, again, because of politics, some countries do, some countries don't focus on that aspect, because you know all the garbage we create with electronics and also now robots more and more, especially when they become into their lives more and more, there will be really a lot of garbage. And also, you know, so we mentioned also the intelligence of these machines. Of course, there are always open issues about intelligence. What is there are two aspects we look at. One is physical intelligence, as I mentioned, how to embed it into the body of the robots. The second is computational intelligence, like machine learning and AI fields. Those will be continuing and they will be always there. Because intelligence is so complex notion, there is not even definition of it, that since we like to have these robots to be autonomous, they need to have their own low-level and also high-level intelligence to make some autonomous decisions, actions, and learnings, and all these things, adaptation. And that's still always a premature field. Really, if you look at in overall robotics field, there are so much things still not so mature yet. And that's why we don't see too many examples of robots in our daily lives, because they are really more work in structured environments or work in very specific problems, great. But you know, one big thing also will be, and which is already, is medical robotics. So how to make these robots functional and useful in medical applications. This could be in many different perspectives. That I see a big opportunity of having robotics to have a positive impact in our lives rather than ethical questions of autonomous machines. Is, as you know, is a great field, but there are a lot of also ethical discussions we have in our institute and everywhere. Those are all challenges. And again, just be aware of them. And the next things will come up is environment friendly, energy conscious, more intelligent, and more robots working on structured environments. But whatever the buzzwords we will hear, you'll see. But the essence of the problems will be always there. And whoever solves that, those research questions will have a great contribution to our field. And yeah, and there are so much to contribute. So that's my point.
I totally agree with everything that's been said here. I think that one of the things that we can start to think about more, and that I think people should be studying more, is what happens with these downstream applications of the soft robots. So like a main driver of soft robotics research is, okay, we'll be able to operate more safely with humans. But humans have to accept and trust these robots in order to use them. And so if we think that they're like creepy and gross or weird, then that may not happen. We may not want like a tentacle robot to do our dishes for us, right? So I think that not only should we be thinking about humans interacting with soft robots, but we should also be thinking about animals interacting with soft robots. So I'm doing work now in animal-robot interaction, and I think that it's already shown me how these applications can drive innovations in soft robotics and help kind of achieve these kind of stepping stones towards these really impressive future applications and incorporation into everyday life. Having these unusual or like esoteric, weird experiments that you want to perform as a biologist you may need some very specific functionality. And that is something that can drive innovation in the robotics world. And you never know where that's going to lead to. So I think that looking at these applications of downstream, like looking at HRI, looking at ARI, maybe animal robot interaction, I think that that's something that can complement soft robotics and help it to succeed far into the future.
Thank you. All right, so I'm looking at some of the audience questions, and there's a few about ethics. So I wanted to know what the panelists think the most pressing, again, one of these big questions here. What's the most pressing ethical concern for robots composed of synthetic materials that biohybrids or biomimetic robots could address? Or you can choose to answer this question in the reverse way. What's the most pressing ethical questions for robots composed of living systems made of living materials? And how can biohybrid and biomimetic robots address these problems? I forget who's next. Who wants to take this one? Who wants to be first on ethics?
I can start.
Sure.
Just to get it out of the way, really. No, I actually think that this is, the most important social thing that we need to consider when we're working on this field. And I also think that we need to get comfortable talking about it, not only to each other, but also people outside of the discipline. And I've tried to do it in the past by sort of constructing these stories or vignettes of like, oh, I've told you all about this cool robot and how it can help somebody walk again after they've lost a leg. But, what if I made that muscle too strong? And now you have this super strong muscle, and now people are chopping off their legs so they can get this super strong leg, and then the whole world divides into super strong people who are rich, and it just builds up and builds up, and we all have these conversations, and every time I have the conversation it goes differently, and people obviously based on their different cultural backgrounds or religious or political affiliation might have a different sensation. But I think you're never going to get a consensus, but you do often get to a where like most people would not cross this. And I think that sort of line can help you sort of define the boundaries of like what is useful, what are people actually interested in focusing on. That being said, in terms of like the actual scientific ethical questions I think we need to ask is when you don't have a standard definition of life or like a definition that everyone can agree on, you have to start thinking, at least in biohybrid materials, just because you're building with something that is living, does that mean that the thing you build is alive? And that question, I think, is really requires a lot of thought. I think there's obvious cases where when I'm building something that's like a robot that's using muscle to walk, I'm like, well, this isn't really autonomously metabolizing products in its environment. It can't reproduce itself. It doesn't really have a conscious, and it's very obvious to me. But when I start thinking about integrating control elements, say like motor or sensory neurons, there is going to be some point when it's not just sensing stretch, but it is sensing stretch that is more stretch than it wants to feel, and it is processing it in a way that mimics pain, right? Like it is possible, it is maybe 50 or 100 years from now, but it is possible that we could get to something like that. And then you start thinking about if something can feel pain, is it something that should be regulated in the same way that we might do animal research? And also one more thing I will say is that when you're building with biological materials, the provenance of the biological materials is very important. And so, we have obvious examples of things like Henrietta Lacks and the HeLa cells that were taken from her without her consent or knowledge of what would happen, and her genetic information has been shared around the world. And like, that's a sort of thing where we know it's bad, but people do it all the time. They take genetic tests all the time that are telling people things about, their family, and they're going into some big data reservoir. So if we don't cultivate literacy about what it means to donate cells to something, what it means not only for yourself, but your family, not only now, but 50 years from now or 500 years from now, that I think is also a really big ethical question of teaching people what is ownership of biological materials, not teaching, understanding together. What does ownership of biological materials mean? I think that's another big question also. So there, I said it, now I can walk away.
That was excellent. Thank you, Ritu.
Okay, I might maybe chime in. I mean, any technology has always, we design them for any given use, and they can be also used in many different ways that can be against, human safety or other ways. So that's why this is a general ethical question of like, what you design and build technologically as a robot or whatever, how it is used is really important. And that's one aspect we always have big challenges in AI robotics. I mean, how they can be dangerous to human lives, how much data privacy, and it can also have as challenges watching people, and a lot of issues are coming up more and more when we have drones around and many things. So those are issues that we need to really actively be involved in these discussions as researchers, rather than saying, look, I developed my technology and you guys use it as you want. That's, I think, not ethically correct approach. So that's why we need to really be aware of what are the potential uses. I mean, we develop wireless medical soft robots, but someone can take the same robot and do torture to people or do other things that might come up that you never imagined even. So we need to think about these things all the time and be actively questioning and hopefully try to have even some power to decide where they can be used, which is a big ethical question and challenge in all of the fields of technology these days. And more animal rights. I mean, in biohybrid is one interesting field that I observed a lot. I mean, combining live cells are okay, but even there you need to be careful if it is human cell or any specific cell type, that you need to be very careful how you extracted that cell from a person. And then second is, there was some projects that are still maybe that people took insects or real animals and put neural probes into the brain and start to control these organisms as they want. That is one of the hardest ethical questions, projects that you can imagine, like how can we play with the living animals? How much can we, and which animals are okay? So funny thing is there are a lot of animal rights related constraints in our research, but if you look at insects and many organisms, they are okay. There are no legal protections, but still I think there are all these questions of, are they right to do play with those things in that way? Yeah, I mean, these are things all coming up that we need to actively be involved and solve. And there is no easy answer.
Cecilia, would you like to go, or do you want me to go?
You can go first if you want. Yeah.
Okay, thanks. Yeah, so I definitely agree with what Ritu and Metin both said. I think that, so I've been working with rigid robotics and soft robotics, and I'm finding soft robotics to be a lot more wasteful than rigid robotics. Because when you have rigid robotics, you have some of these standard parts and tools, right? So you have your nuts and your bolts and your like circuit boards, and if a robot breaks, you can break it down into its component pieces and often reuse them and build something new. But like, for example, the work that I do in soft robotics depends on pressure, right? So building up pressure inside of a soft system. And once you have an aneurysm, that robot no longer works, and really we can't repair it as far as we know right now. And so we kind of have to throw it away. And so it's generating a lot more waste than what a rigid robot would do. And so if we can find some way to learn from the biohybrid folks and learn about, how to break things down, how to reuse them, repair them, or heal them, I think that that's one way that we can be more ethical about the way that we do this research in the future. The other thing too is I think when biohybrid as an approach scales up in terms of size and organismal complexity, just as Metin said, if you're kind of controlling a whole organism, then it becomes much more ethically challenging. And so I think that it's something that is like totally valid to do at a much smaller scale, but I think that we do need to think about, I mean, when I was taking classes in vertebrate surgery at a medical school, they were saying, you know, we have to actually understand how animals feel pain and how they understand suffering. And we have to recognize that so that we don't cause undue suffering, right? And all of the animal experiments that I do, they have to be reviewed by a board of animal care and use. And so it's really important as we move forward that we consider animal pain and animal suffering and different, you know, in the animals that are different from us, and these different experiences as we go forward and think about how we're incorporating our designs into nature.
Yeah, I don't have much to add. I'm also not in the biohybrid field, so I'm probably not the best person to elaborate on the ethical issues there, but I agree with what was said, and the issue of the dual use that Metin described so well is definitely one of the ethical issues. And for me, that again, I'm not in the biohybrid field, and for me, an issue is where does this living material come from? And that was a bit touched by Ritu actually. So yeah.
Can I have a small anecdote about these cyborg robots? That was a big project in US, and engineers could manage to put neural probes to the brain of a beetle so that they can control left and right. But the funny thing is, when the beetle saw a female pheromone, they couldn't control anything anymore. So in nature, there are still dominant other behavior that we cannot really manipulate as we want. And I think we should, of course, not manipulate it at up to some point. But that was funny.
Yeah.
Okay, we're getting towards the end of the debate, and I realized that we didn't quite frame this too much as, which I appreciate this. It wasn't so much bioinspiration versus biohybrids. I'm not sure how useful that versus distinction really is, but for the sake of the poll question, I'm wondering maybe if we could try to drive up the responses towards biohybrids. I think the winner of the poll was bioinspired robots were preferred. So I'm wondering if we can give some reasons why we should incorporate cells into robots or other living materials that already possess the desired properties that we seek in robots, to try to convince some of the field that maybe this is worth pursuing. Let's start with Ritu, the expert here. What do you think about this? How would you convince some of the skeptics here that actually we should be using living materials in our robots?
I don't know, maybe I'll just start crying and be like, why have you made me waste my entire career? No, I won't do that. I'll save that till later. But you know, I think that we're not in opposition, right? And I think the whole point of biohybrid design is not to say throw away soft robotics, throw away bioinspired design, throw away hard robotics, but to say that to neglect this huge set of materials that we have available to us that we can build with, just because it's too hard to build with them right now, would be a big mistake. And that's what I hope that I can try to convince people. It's like biohybrid means biology plus other stuff. Other stuff is still valid and still exists and is still a thing, but there are things that biological cells and tissues and organs can do that, you know, synthetic materials just can't do, and maybe they can do in 100 years or 500 years, but we have these materials available to us right now. and we can start leveraging them. And I gave the example, for example, of the chemical factory or living cells that can sense and respond to changing sugar concentrations and secrete insulin. Those sorts of approaches are also very valid for other diseases. Everything is caused by biochemical and electrical dysregulation, and if you can create biological systems that can sense and process and respond in either electrical, biological, chemical ways, you can address all of these issues. And in those programmings, those inner tools already exist in cells and tissues. You don't need to go in and say, when you sense this, like do this, do this, do this, do this, and 500 steps later you get this. Instead, you can just say, cell, I can genetically engineer it, or it already does this thing where when I stimulate it like this, it's going to get stronger. Does it? I made a robot that's stronger without understanding the biochemical mechanisms by which muscle gets stronger. And I didn't need to do that, right? Because I already knew that if I stimulate it over and over again, it's going to get thicker and stronger and bigger. It doesn't matter why it did it, but it did it. And it did something no synthetic material could do before. And the same thing goes for the robots that we made that healed. Do I understand everything about how satellite cells in our bodies are trafficking to the site of damage, or how the immune response is responding to damage? No, I didn't know all of those things. But knowing some basic principles of if I use these materials, they'll be able to proliferate and heal damage over time, I was able to make the first robot that could heal completely from damage, right? So I think that's what I'm trying to say is that there is no opposition, but there is a question of me saying, like, how can you neglect all of this stuff that's here and like all of these materials we have available to us? I think it would be silly to do so, and maybe I'm wrong, and that's fine too, because that means that the problem has been solved using some other mechanism. But I think to not even try it, to not even feel like it's a valid approach, would be a big lost opportunity for all of us. So hopefully that will convince a few people, and if not, I'll just start crying and hope for a pity vote where they're just like, well, this poor girl, let's help her out.
Thank you. Yeah, perhaps it was a poorly phrased question. I did find the poll though, and it is twice as many people thought that biorobotics should not directly incorporate living materials instead of bioinspiration. So Metin, I'm wondering if, yeah, Talia, do you have something that you'd like to add?
I was just going to say that the poll, the way that it's worded, is that we should be foregoing bioinspiration and only work on biohybrid. If you say yes to that, it's like eliminating an entire field, right? But if you say no to that, then they can coexist. So that may be why there's so much in the no column, right? It's not saying we should forego biohybrid and only do bioinspiration. That's all.
That's fair. Yeah, it was weighted asymmetrically, I think, towards bioinspiration. Metin, what do you think? If this really were a debate where you're trying to convince someone to use living materials, what would you say?
Yeah, as I said, please don't be conservative. Look at all approaches, and biohybrid is definitely one of them. And I'll tell you why really biohybrid is promising in some of the problem solving. In our group, we work on medical, what we call micro robots, which are cell scale, that is very small in the body. And one big area is cancer therapy. As you know, we have a big problem in cancer and also other infectious diseases these days. So always the question is, how can you take a targeted drug, or, I mean, also Rita mentioned, like cells and many cargoes we call, to a target location in the body and fight against cancer. In my group, we have the synthetic people who are fully solving the problem synthetically, and there are biohybrid guys. And why we have both? Because each approach has pros and cons. And let me tell you why biohybrid is very promising and maybe even better than synthetic right now is because what we do is now we take the patient's immune cells. Let's say that you have cancer, we go and we take your some immune cell sample from your bone marrow and macrophages of the same person. As you know, immunotherapy is now being established, a popular technique now. So we take the macrophage of the given person as a soft cell, because the nice thing is if you take that macrophage and engineer and put back to the same patient, immune cells of the patient will not attack you. If you have synthetic material, anything in the body is attacked by our immune cells. So that's evolution, how we try to get rid of all the foreign objects. So if you take the real cell that is taken from the patient, which is live, a macrophage, which is also active, it can crawl around. So the great thing is immune cells don't attack, which is a big problem for our synthetics. The second, macrophage is so smart. It can know where there's a cancer. It can feel it. It can sense it. It can go in the blood vessels with a much easier way than our synthetic robots. And then when it detects the cancer, can stop there by sticking there, but better, and change the mode and penetrate the tissue. It's very hard to do that synthetically. How to penetrate the cancer tissue is one of the biggest problems. But macrophages can do it if you can integrate them with our synthetic biohybrid approach. So there, I see that for cancer therapy, that kind of problem, the macrophage soft basically cell integrated with our synthetic other materials, you can control macrophage behavior, is really promising now for cancer therapy in the local efficient way. So the second example, bacteria. You know, bacteria are typically pathogenic in our minds, but they are not, as we know in our microbiota now. We have a lot of bacteria helping our digestion, even it helps your psychology and many things. So, and one important thing also they discovered 100 years ago is bacteria attack cancer cells if you choose the right bacteria type. So that means if you take the live bacteria, that's what the vaccine is. Come on, guys. Vaccines, they have live, tamed, already, you know, bacteria against bacteria things. And I mean, basically, they are tamed and much, of course, not pathogenic, but they are live. And that way our immune system can recognize, and that way we can react. So that's why I see a lot of potential in the bacteria therapy, for example. When there was a patient that was had a throat cancer and the guy would die, the doctor 100 years ago injected a special bacteria, which the doctor tamed the bacteria by heating and a little bit making it not active. And that injected bacteria saved the patient's life who was dying. So now there's a big field of research called bacteria-based cancer therapy that we are now taking live bacteria, integrating with our synthetic, again, control systems that we can really control how they can treat the cancer. So in that sense, in medical fields and in some specific fields, I feel that biohybrid approach will be really one of the best solutions. That is at the cellular scale, attacking cancer, helping for immune system, also control like vaccination and many other things. There I see there is a big winner approach that is really useful, so we shouldn't give up. In the larger scale robots and other systems.
Well, then I think we're running out of time, but,
yeah, sorry.
But thank you. That was a great defense. I think you have swayed the poll a little bit. I want to give time to Cecilia and Talia just for some closing remarks. Maybe they'd like to emphasize something that was an important part, but was kind of complex. Anything you can use this time however you like. Cecilia, why don't you go first, and Talia.
Yeah, I make just one more point that we didn't touch, but I think it's important and it's also relevant to the latest discussion on biohybrid. So, to what extent are they programmable, controllable, and programmable? I mean, controllability and programmability is really at the core of robotics. This is an issue that is true for many other artificial things like smart materials. I mean, there are fantastic materials, but to what extent are we able to control their behavior and to program their behavior? And this is also the question that I refer to the biohybrids, and I think this is an important point.
Yeah, I will just emphasize again that I think that if you vote no in the poll, then the two fields can coexist and actually learn from each other, and probably new ideas will emerge that wouldn't have been possible if we just isolated and had one field or the other. So I think that no is the right answer here in this poll, but. I think that there's so much we can learn from the biohybrid approach. I think that we can learn so much more about healing and learn about kind of biodegradability and how we deal with our waste. I think that at the cellular scale, I think the biohybrid approach definitely excels. I think it's really exciting to think about the actions that we can have at that scale. But at a larger scale, I think that the bioinspired approach is definitely the way to go. So if I think about taking kind of a biohybrid approach at a larger scale, then maybe if I'm doing my field work in the jungle and I see a parrot maybe like opening a shell or opening something like that. As a bio-inspired biologist, I might say, oh, this is really interesting. I wonder how the parrot was able to do this so well. And so I study the animal, I learn how the animal works. I might, take some CT scans and build something out of completely new materials that works and is durable at that scale. And then I have like a better bottle opener, right? But maybe a biohybrid approach, I'm not sure what that would be, but maybe it involves like getting a pet parrot and then like asking the parrot to like open the bottle for you. Or an even more gruesome approach that I don't think anyone would take is like if you find a dead parrot on the street and then you find a way to like actuate the beak that exists already, right? So I don't think it's that valid, ethically valid at an organismal scale yet. So I think that it is really important to be doing both, to be doing them in parallel and to be communicating with each other, because I think there's a lot we can learn from each other and the world is a better place if we do both in parallel.
Thank you so much. So I'm afraid that's all the time we have for the debate. I'd like to thank our panelists. I'd like to also thank the organizers, Marwa, Hadi, and Laura. We have the poll question that just came up again, the controversial poll question. You can answer C, undecided, if you'd like. And we'll take that to mean that both are good. Happy Monday, everyone. I'm Sam Kriegman, and that's it.